Good morning, all. This is Monish from RV College of Engineering. My USN is 1RV21MB052. This video is part of my experiential learning for the subject robust design. Here, I'll be conducting regression analysis, Taguchi design, as well as one-way ANOVA for calculating the best economy of the Splendor bike possible. Now we have the Splendor bike, which is also known as the mileage king, as it is so economical. For the experimental details, our aim is to find the best weight, RPM, and speed at which the bike gives out the best economy. The fuel economy and mileage are both ways to measure how efficiently a bike uses the fuel. Uh, to be proper, mileage is actually the odometer reading, but in technical terms, the economy is the one which we have in kilometers per liter. Apparatus which we'll be using, one is the bike, Splendor bike, and then fuel, we need to have 900 ml of fuel, 100 ml for each trial. We'll be conducting 9 trials, and then a plastic bottle for filling the fuel. Procedure: first we drain the complete fuel by removing the tube while keeping the position in on. Then we insert the tube back. We then fill 100 ml petrol in the tank. Then we record the odometer reading. We then run the bike till the bike stops due to the petrol being completely used out. Then we record the odometer reading again. Therefore, the total distance traveled will be the odometer reading in step 6 minus the odometer reading in step 4. That will actually be the distance traveled in bike for 100 ml of petrol, because for each trial we'll be just using 100 ml. Therefore, the distance which it travels will be the distance it actually has traveled in 100 ml of petrol. Therefore, for 1 liter of petrol, we multiplied the value which we got the distance by 10. Therefore, we'll get the total distance it can travel by considering all the factors in 1 liter. We then repeat the steps from 3 to 9 for each trial. This is the off position. If the knob is horizontally placed, then it indicates off position. Then this is the on position if it's vertically placed. And this is actually the tube. In the step 1, we need to drain out the fuel completely. Therefore, there is a clip here. If we press it, it gets elongated. Therefore, we can easily remove the tube, drain out the complete fuel, and then put the tube back, insert the clip, and then we keep on adding 100 ml for each trial in the petrol tank. This is the odometer reading where we record the odometer in the sense how much distance has the bike traveled in 100 ml of fuel. Therefore, from this we can get to know how much distance it has traveled. This is the tachometer. At what RPM is the engine running? We are considering 3 factors. The 3 factors are: one is weight, which is measured in kg; one is RPM, which is revolutions per minute of the engine; and then the speed, which is kilometer per hour. Then we are considering three levels for each factors. 3 levels for each factors, which is weight. We are considering 60 kg, 140 kg, and then 160 kg. And then RPM, which is 2500 RPM, 3000 RPM, and 3500 RPM. And then speed, which is 40 kilometer per hour, 50 kilometer per hour, and then 60 kilometer per hour. To compute this, we have prepared the table, which is here. Here it indicates 3 factors, which is weight, RPM, and speed, and their levels, which is 3 levels: L1, L2, and L3. Here are tabulated it. Next, we need to find out the Taguchi L9 array. For this, we'll be using Minitab software. Therefore, in Minitab, we first go to Statistics, Design of Experiments, Taguchi, Create Taguchi Design. Now we have 3 levels. Therefore, we'll be choosing 3-level design. And the factors, we have 3 factors. We'll be choosing the number of factors as 3. We then need to select the design. Therefore, for 3 level, we have L9 and L27 available. we'll have to choose L9. We choose L9 and not L27. For choosing the L9 array, we need to go to factors. In factors, we have A, which is weight in kg. Therefore, we name it as weight. Weight in kg. And then the factor B, we have it as RPM. And then the factor C is speed in kilometer per hour. We need to type in the levels. Therefore, for weight, it is 60, 140, and 160 kgs. 60, 140, 160 kgs. RPM, it is 4,500, 3,000, and then 3,500. Speed, it is 40, 50, and 60. 40, 50, and 60. Let us check once again. Factors are weight, kg, RPM, speed in kilometer per hour, weight in kg, RPM, speed in kilometer per hour. For weight, it is levels 60, 140, and 160. 60, 140, and 160. For RPM, it is 2,500, 3,000, and 3,500. Speed is 40, 50, and 60. Speed is 40, 50, and 60. After choosing the factors and putting in the values of each levels, we click OK and then OK here. Therefore, we get that in the table here, which is weight, RPM, and speed. This is the L9 array. Therefore, we have 9 rows. For that, our response will be economy, which is in kilometer per liter. Therefore, for which I have conducted the trials, I've stored it in an Excel sheet. This is the value which we get for the L9 array. Therefore, when I conducted the experimental trial for 100 ml, this is what I got. Like for the first trial, I got 5.988 kilometers per 100 ml. Therefore, when we multiply by 10, we get 59.88. Therefore, for each liter, the bike runs 59.88 kilometer in the trial 1, which is this one. In the same way, we will have to conduct for each trials. Totally, there are 9 trials. So now we copy this column and then paste it here. After filling in the response column, we go to statistics, design of experiments, Taguchi, analyze Taguchi design. Here, the response data is in C4 column, which is economy in kilometer per liter. We select that. We go to graphs. We generate the plots for main effects and interaction in the model for. We can select even standard deviation. These are our factors. Display response tables for standard deviation also. This is nothing. For options, our response is economy, for which we need to have, it's better if we have more economy. So we choose larger is better. And then we click OK. So now we have got the response table for signal to noise ratios. for which larger is better. Obviously, if we are considering economy in any vehicle, we always look for the best vehicle which gives the highest economy. So that is the reason we have chosen larger is better. Therefore, we have three levels and three weights. They've given the delta, which is the change in weight. Therefore, we have the rank 1, 2, and 3. Therefore, in signal to noise ratios, weight is given rank 1, RPM is given rank 2, and speed is given rank 3. For the means, it is also the same ranks. First one for weight, second one for RPM, and third one for speed. This is the main effect plots. Let me enlarge this. This is the main effects plot for means. Here first we have weight, then RPM, then speed. At level 1, we have 60 kg, for which we have mean of means on the column. In the same way, for each level, the graph has been plotted here. The same way, we have main effects plot for ascent ratios at level 160, at level 2 140, and level 3 160. Similarly, for RPM and speed, the graphs has been plotted here. Next, we can also conduct regression analysis. For that, we need to go to statistics, regression, fit regression model. Here, our response is economy, which is in C4 column. Select. Our predictors or factors is weight, RPM, and speed. So we select all three. Weight, RPM, and speed. We select all three. Weight in kg to speed in kilometers per hour, which is from column C1 to C3. Then we go to model. Nothing in model. Options. Nothing in options. And then graphs. In graphs, we'll select normal probability plots of residuals. Okay. And then we click OK. This will generate the normal probability plot, and ANOVA table will also be represented here. We have the regression equation, which is economy, which we get from the bike in kilometer per liter, is 67.29 minus 0.03225 into weight, which is in kg, minus 0.002263 into RPM, minus 0.0012 speed, which is in kilometer per hour. We have the coefficients here. This is the ANOVA table. We have the source, which is regression, and then we have three factors, which is weight, RPM, and speed. We have the error and then total. This gives the degree of freedom column, and this gives the sum of squares. This gives the mean of squares. This is the F value and P value. We have normal probability plot here. This gives the percentage and residuals. This indicates, like, this is the plot of the each point, each trail. This points indicates the each trail. Now we can even do a one-way ANOVA. For that, we go to stat. We conduct one-way ANOVA. A response is economy factor. For one-way ANOVA, we can choose only one factor each time. Therefore, first we select weight. We click OK. Here we generally, in analysis, we always choose a null hypothesis. Here we say that all means are equal. In alternate hypothesis, which is H1, it says not all means are equal. We are choosing the significance level as 0.05. Here we have the factor weight. It has three levels, and then the values are 60, 140, and 160. This is the ANOVA table. We have weight, error, and total, a degree of freedom, sum of squares, mean of squares, F value, and P value. This is one-way ANOVA plot for economy versus weight. In the same way, we can have one-way ANOVA for the next factor, which is RPM. Here also it's the same thing, null hypothesis, alternate hypothesis, significance level. We have the ANOVA table here, and this is the plot for economy versus RPM. Next, we can conduct one-way ANOVA for the last factor, which is speed. This gives the method and then ANOVA table, and then the interval plot for economy in kilometer per liter versus speed. This is economy versus speed. So this shows one-way ANOVA considering all factors. And then we did regression analysis in which we got regression equation as well. And then starting we found out L9 array using Taguchi design. Now we shall see. This is Taguchi's array, which I showed you earlier. And then this is a response for Taguchi's array, which I have conducted the trial and then got these responses. Now we shall see the genetic algorithm. This is a Python. In using genetic algorithm, we can find the best economy which the bike can deliver. So we have the factors and levels here. Speed levels, which is the first factor, we have 40, 50, and 60, which is in kilometer per hour. And then we have the RPM levels, 2500, 3000, and 3500. We have the weight levels, 60, 140, and 160 kg. Here there is population size, generations, mutation rate. Then this is the L9 array from the Taguchi's design. Next we define the fitness functions. We have weight, speed, and RPM, which are individual. And then we define the we initialize the population. Then we parent selection, tournament selection. We select parameters in which we define the population and range as well. We have crossover, single point crossover. We define the crossover and then mutation to random flip one of the factors here. Then this is just the code where we have if it's greater than or less than, it is like a cyclic loop in which it will compare if it's greater than or less and gives the best mileage which the bike can achieve. After running this code from the start till the end, after running this code in Python, we get the best economy as 59.88 for which configuration? For the configuration which is weight, which is 60 kg, and then RPM, which is 2500, and then the speed, which is 40 km per hour. Therefore, for these factors at levels 60 kg in weight, 2500 in RPM, and 40 km per hour in speed, we get the best economy as 59.88. Thank you.